Hello. Today we are going to present to you Fermat's little theorem. Pierre de Fermat was a French mathematician who was also known as the founder of the modern theory of numbers. He was also one of the greatest mathematicians in the history of mathematics by making major contributions such as for the invention of calculus, co-inventing geometry. He invented the probability theory alongside the famous mathematician Blaise Pascal, and also other major contributions to number theory. His first important contributions to mathematics was with the new methods of finding maxima, minima, and tangents. Fermat lived with his father, who was a successful, wealthy businessman who dealt with agriculture products, and his mother, whose family was an aristocratic family. She died when Fermat was only 7 years old, but nothing is known from his early education since there were no records suggesting it. Being from a wealthy family, he received an excellent education but also had the ability to speak multiple languages, such as Classical Greek, Latin, Spanish, and Occitan. He went on to study civil law at the University of Orleans and graduated when he was only 18. He then moved to the city of Bordeaux, where he became an attorney in the High Court. After his father died, Fermat used his inheritance to be able to get a senior position in the High Court. A year after, he married his cousin Louise Delon, who was only 15 at that time. They had 8 children, 5 of whom survived to adulthood. He is mostly remembered for the Fermat's little theorem. Fermat's little theorem is a fundamental theorem in elementary number theory which helps us understand how to compute the powers of integers, modular prime numbers.
Fermat's little theorem can be stated as follows. Let p for any natural number be prime, and let a for any integer, such that p does not divide a. Then we get a to the p minus 1 is congruent 1 modulo p. Here is a quick example. 2 to the 5 minus 1 is equal to 2 to the 4th, which is equal to 16, which is congruent to 1 modulo 5. However, given the theorem, we can change this to make it more manageable by multiplying both sides by a. This changes the theorem to look like a to the p is congruent to a modulo p. We can still get Fermat's little theorem from this congruence by canceling a, which we can do if p does not divide a. We will now begin to prove this theorem by using a proof by induction. Our base case is for a equals 1. 1 to the p is congruent to 1 modulo p, and this is clearly true. 1 to the power of anything is 1, which would leave a remainder of 1 modulo p. Our next step is to make our assumption. We are going to assume that a to the power of p is congruent to a modulo p. Using this, we can move on to our inductive step, which is where we will begin to prove this theorem. We will be using the binomial theorem to prove this for a plus 1, meaning we should end up with a plus 1 to the p is congruent to a plus 1 modulo p. And we will now use binomial expansion on a plus 1 to the p. Binomial expansion on a to the 1 plus p looks like a to the p plus p1 a to the p minus 1 plus p2 a to the p minus 2 plus all the way up to p to the p minus 1 a plus 1. Note that p divides into any binomial coefficient in the form of pk for 1 is less than or equal to k is less than or equal to p minus 1. And this follows by the definition of the binomial coefficient as pk equals p factorial over k factorial parenthetical p minus k factorial. Since p is prime, then p divides the numerator but not the denominator. When taken mod p, we lose the middle terms of the previous binomial expansion and we end up with a plus 1 to the p is congruent to a to the p plus 1 mod p. And since we assume that a to the p is congruent to a mod p, we are left with a plus 1 to the p is congruent to a plus 1 mod p, which is what we were trying to achieve. Therefore, this holds true.
We can use Fermat's little theorem to find reminders of large numbers. So to find 3 to the power of 31 mod 7. We can do it easily by hand using this theorem. And we know that 7 is a prime number, so we know that 3 to 6 is congruent 1 mod 7. We can raise both sides to the power of 5 and then multiply it by 3. Thus, 3 to the power of 31 is congruent to 3 mod 7. We can also use Fermat's little theorem to check if a number is composite. To check if 341 is composite, we can raise 3 to the power of 341 minus 3 and check if it's divisible by 341. So we know it's not divisible, thus it's not a prime number, and we can check that 341 is 11 times 31. It doesn't work the other way. If the theorem works, it doesn't mean that the number is prime. Right, that's it for, okay. More real life example is in cryptography. RSA is a crypto system that uses private and public keys. Public keys can be shared without compromising security. So to encrypt a message using this crypto system, we choose two large prime numbers, P and Q, and keep them private. We can choose another large number, D, that is relatively prime to the product of P minus 1 and Q minus 1, which means that it has no common factors with P minus 1 and Q minus 1. Then we compute E from E times D is congruent 1 mod P minus 1, Q minus 1, and we can do it using Euclidean algorithm. To send a message, we convert our alphabetic message into a number M and send the number M to the power of D modulo N. Then the receiver can decipher the message by reducing M to the power of D times E modulo N. From the decryption key D, we know that D times E minus 1 equals P minus 1 times Q minus 1 times K, where K is any integer. Then by using Fermat's little theorem, we have M to the power of D times E equals M to the power of D times E minus 1 times M equals to M times M to the power of P minus 1 times Q minus 1 times K is congruent to M mod N. And this algorithm is used to keep credit cards numbers safe, because credit card numbers are very large numbers, so when they're raised to any power, they're even larger numbers, so it's hard to decrypt the message without knowing the decryption keys.
So another example of how to use this in everyday life is, let's say someone who makes necklaces for their Etsy shop, they could accidentally find themselves discovering Fermat's little theorem. Say this Etsy shop makes necklaces with bead charms, pearls, anything like that. They start with 3 beads, but they do not want it to be monochromatic, so they decide to use 2 colors. When looking at all the possible combinations they could have had with their beads, they remove the combination with only 1 color and make them into rings for the necklace. When they completed all these rings, they noticed there are only 2 major styles or groups, and then having each ring in the respective group almost impossible to differentiate. When wanting to figure out how to make each set of beads look different, we find that we can cyclically shift the group by p times without having to change anything else. So when we look at 2 to the third minus 2, we now divide it completely by p, completing the cyclical proof since the beads have to be an integer. So just to bring it all back together, in this instance, since the beads are the string, we will make that p, while making the amount of colors in the string a. To make these combinations, we write to the third, or a to the p power. But because we are only using multicolored beads, there are a amount of strings with 1 color. We subtract what we have by making subtract what we have by a, making it 2 to the third minus 2, or a to the p minus a. Finally, when seeing that we could cyclically shift the bead p times to have a different outcome, we know to divide everything by p, making it 2 to the third minus 2 divided by 3, or a to the p minus a divided by p. Writing this differently would give us a to the p equaling to a modulo p, which is what we proved earlier in our presentation.